Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, wonderful students of Senior 2. This is chemistry lesson. We are still on unit number 10. Remember about the properties of organic compounds and uses of alkanes. I'm just excited once again to be with you in lesson number 3. We'll be looking at the physical properties, look at the chemical properties, and then finally we'll look at the uses of these alkanes. So that is basically what we are going to look at. But I just want to remind you of some of the things that we looked at in the previous lesson. I hope you still remember, but the most important part that we looked at was the nomenclature, whereby that the nomenclature depends on IUPAC. That is the International Union of Pure and Applied Chemistry. So we said under this union, there are two words that we join together to make the name of the alkane. That is the prefix and the suffix. So the prefix, as an example, if I can remind you, we said there are special words that we use like meth, eth, prop, but, pent, hex, hepta, and so on. And then the suffix is the ending of the name. Alkanes end with A-N-E, N. So that is why all the alkanes will end with N. That is the suffix. And that is, if you have carbon, when carbon is number 1, because you remember the general formula of CnH2n plus 2. That general formula is the one that helps us to write the formula of the compounds. When N is equal to 1, then the first member becomes methane. Meth, which is the prefix, and N, which is the suffix. Then we looked at the isomerism. Isomerism, what did we say is? So we said isomerism is the existence of compounds of the same molecular formula, but with different representation, structurally represented differently. So that is the things that we looked at. And before we look at the physical properties, because we always refer to those compounds that we looked at. So what is the first physical property that we are looking at? We look at the physical state. So we look at the physical state. How does the compound exist? Is it a gas? Is it a liquid? Is it a solid? In which state of matter does it exist? That is we are looking at we are referring to the alkanes. But we should all remember that alkanes contain only the carbon-carbon and carbon-hydrogen bonds. And there are weaker forces that join these molecules together. So the first 4 members, that is very important. The first 4 members from N is equal to 1 to N is equal to 2 are gases. So what are those members? Do you still remember those compounds? Because we are said from carbon number 1 to carbon number 4. So which are these members are we talking about? We said these ones exist as gases. So you need to remember these ones as well, because we said the first member is methane, the second member is ethane, the third member is propane, when the fourth member is butane. So these members here exist as gases at room temperature. From carbon number 5 to carbon number 17. Carbon number 17. So we have not looked at compounds or alkanes with the carbon higher than 10. So we looked at the carbon. The last carbon atom that we looked at was that one with the number 10, which was decane. So these ones exist as liquids. They exist as liquids, whereas the rest of others from carbon-17 and the rest exist as solids. So when you look at this, when you analyze this, you'll see that the compounds, the alkanes with the lowest number of carbon atoms are existing as gases. So as the number of gases, as the number of carbon atoms increases, then you see the state is changing. The state is changing. So it changes from gases to liquids to solid as the number of carbon atoms are increasing. Where we said carbon number 5, that is pentane, we have hexane, we have octane, we have nonane, we have decane as those, so those ones will exist as liquids at room temperature. The rest of the compounds beyond 17, we are saying they are solids at room temperature. So one of the examples that we can give of the solid alkane is the candle wax. The candle wax is bougie. That one we use for lighting, providing the light. So that bougie is one of the examples of alkanes, but with high molecular mass, with high number of carbon atoms. That is why it exists as in solid state. So that was the physical state. The second one that we need to look at is the solubility. Solubility. That is the second property that we have to discuss. Hydrocarbons are non-polar in nature. So you remember when we were mentioning about the covalent molecules, we mentioned about the covalent molecules. So these non-polar molecules belong to the covalent molecules or the covalent compounds. So the non-polar molecules are covalent molecules. And you remember very well the rule, if you look at if you go to the screen, that rule which says the like dissolves like. Like dissolves like. So we have, sorry, we'll just go back a bit. So the like dissolving like, that is one rule that we need to remember. Like dissolves like. So these molecules, the compounds of which are organic and of which alkanes belong to, are said to be non-polar. Water is a polar molecule. So that is why water does not dissolve these organic compounds. Because they are not the same. They don't have the same nature. Water is polar. This is a polar molecule. Whereas these alkanes are non-polar. They are non-polar. So that means this one, because they are not the same. If this compound was also polar, that is, I'm just trying to explain how the rule operates. Water is polar. Alkanes are non-polar. So meaning, because they are not the same, they don't have the same nature, then these ones will not dissolve. When you get water and add an alkane, there will be no dissolving. And this applies to most of the organic compounds. So when we say like dissolves like, for example, if you have water, and then we have also probably like sodium chloride. Sodium chloride is also, this one can also be said to be polar. And this one can also be polar. So that means they like dissolves like. Water dissolves in this because they are polar. Now, organic substances, that is alkanes in specific, to be specific, organic compounds are non-polar. They don't dissolve in water, but they dissolve in other organic compounds. they dissolve in other organic compounds which are also non-polar. For example, if you have any of the alkane, maybe hexane, this is the one that exists in liquid form. This is non-polar. Now, if we have another compound that is non-polar, any other liquid that is non-polar, will dissolve this one. Now, we can give, there are so many examples. We have ethers. These are a group of compounds that are also non-polar. So they are also non-polar. They will dissolve. We may have methylbenzene. Methylbenzene. This is one other example of non-polar molecules. Non-polar molecules. So this is like, so the like dissolves like. That is how the rule operates. So organic compounds, alkanes in particular, do not dissolve in water, but dissolve in other non-polar molecules. These are some of the examples. We can talk about the carbon tetrachloride, with C4. This is also non-polar, and so many other non-polar molecules. So these ones will dissolve in alkane, but they won't dissolve in water. So that is about the solubility. So we can also talk about the boiling points. And as we have mentioned from the homologous series, that some of the characteristics that we mentioned about, so we said there is some gradual increase in these physical properties. So the gradual increase in the physical properties such as the boiling point and melting points. So there is some increase as you move down. As the number of carbon atoms increases, then there is an increase in the boiling point. So as the compound becomes bigger, so the intermolecular forces increase, and therefore the boiling point and the melting point will also have to increase. So this is the table that is trying to look at the table on the screen. It's mentioning in the first column here, we have the examples of these alkanes. Then we have the formula and showing even the state at room temperature and indicating the boiling point, the melting point, and the density. So when you look at these compounds, the boiling points, you see there is a gradual increase. Similarly, the melting points also increases in the same way as the number of carbon atoms increases, and as well as the density also increases. So this depends on the intermolecular forces. So as the carbon atom increases, then you'll have increase in intermolecular forces. So those intermolecular forces causes the slight increase in the boiling point. So that means extra energy will be needed to break down those forces for the compound to change into the liquid if it is in the solid, or to change into the gas if it is in liquid state. So the density follows the same order, 0.55. As you move down, you see there is gradual increase in the density. So from the gases to liquids and then to solids, it is very clear there that the solids are supposed to be more heavier when you compare them with the gases. So that is why you see the density is increasing. And we've said the density also follows the number of carbon atoms, which also depends on the molecular mass, and which in turn depend on the intermolecular forces. So that is the density that we have been talking about. So when you look at the density, you'll find out that this is the cane, this is the solid one. You'll find that all these ones that we have looked at, are less dense than water. These ones that we have, they are less dense than water. So that means they are, as you move to down, whether they are even in the liquid state or in the solid state, you'll find their densities are less compared to that of water. So that is density as well. Then let's look at the chemical properties. As we have mentioned earlier in the previous lesson, we said these alkanes are circulated. But they contain only strong carbon-to-carbon and carbon-to-hydrogen bonds, as we looked at some of the examples. So they are quite less reactive, and they are known as paraffins. And this word is derived from this Latin word palam, which means little or less, and affinis, which means reactivity, so less reactivity. So they are generally called paraffins, and that is where the name is derived from. The name derived from Latin tries to explain even the nature of these substances. They are less reactive, from palam affinis, which means less reactivity. They are generally inert to acids, bases, oxidizing agents, and so many other substances. So we have said they are less reactive. But under certain conditions, they can undergo some few reactions. Like, for example, the first one is combustion. So look at the combustion reactions. Combustion, this is the reaction with oxygen. So they can burn in air or in oxygen, either in plentiful supply of oxygen or less supply of oxygen. The gases can, these substances can burn to produce the flames and heat. And for that reason, that's why they are used as fuels. For example, if you have methane, you remember methane, we said it is CH4 plus the oxygen gas. This one will produce, that is under complete combustion. So say complete combustion. Complete combustion means excess oxygen will form carbon dioxide plus water plus the heat. So this heat is given in form of flame, and we are saying this is the reason why these substances are mostly used as a source of fuel. So we look at that one in some in our examples or in the uses that we'll have to look at later on. So you can balance the reaction, as I said earlier, that whenever you write the equation, you need to balance the reaction. Carbon here is one, this is one carbon. You have 4 hydrogens, but here you have only 2 hydrogens. So you need to balance the hydrogen atoms. And that means how many oxygens? Here we have 2, whereas here we have 2 and 4. So you'll need a 2 there. So these are gases. This is complete combustion. But even in less supply of oxygen, these compounds can as well burn. If there is limited supply, either carbon monoxide and water, plus less heat. The heat is produced, but not the same amount of heat that is produced. Or you can have methane plus oxygen giving carbon and water. So these reactions are also possible in less supply of oxygen. You can have either carbon monoxide or you can have carbon being formed. This would be in solid form. So this is some of the examples that we have written down. One, we are seeing So that is the formula that can help you to balance the reaction for the combustion reactions of these alkanes. You can use that formula over here. This is the general reaction that you can use to balance the reaction for the complete combustion. So we have, you see the amount of heat that is generated to 890. That is 1 more kilojoules of heat. That is too much heat. 1 more of methane under complete combustion produces this amount of heat. So this is a lot of heat that is generated. So in the absence of limited supply of air, we said carbon monoxide is formed. Of course, you know carbon monoxide is very poisonous when it is inhaled. So we mentioned even that even carbon can also be formed. And this carbon is a source of the carbon black. This carbon that is formed under incomplete combustion is a source of the carbon black, which we, if you remember, probably know. Sorry, that is, the carbon black is one form of amorphous carbon atoms. So the carbon atoms exist in different forms, and this is one form of carbon, which is carbon black. So it is formed when there is insufficient oxygen. When the insufficient oxygen combines with an alkane, therefore carbon is formed. But it is very important. It is used in manufacturing ink, in printers ink, in black pigments, either the shoe polish and filters of the vehicles. So it is very, very important as well. So the other reaction that we need to discuss is halogenation. Remember I said these compounds are less reactive, but under certain conditions, they can react to form other compounds. So halogenation is the addition of halogen. Halogens are group 7 elements. They are group 7 elements. These reactions involve, so you have halogenation. So this halogenation reacting with an alkane, this reaction doesn't take place at room temperature, as we have mentioned. This reaction takes place in presence of ultraviolet light or in presence of heat. And this will give halogenoalkane plus the hydrogen halide, So that is the compound that is the general name of the compounds that will be formed. So these are some of the examples. So what we only need to note, just look at the screen. What we only need to note is that these reactions are substitution reactions. Just look at what is happening here. You see the methane over here with 4 hydrogen atoms. When it reacts with chlorine over there, you see the chlorine there, then one hydrogen here is displaced by one chlorine. So the other hydrogen displaced forms hydrogen chloride. So that is the chloromethane that we have, that is the chloromethane that is formed. So this reaction, so the reaction is continuous until all the hydrogens are being substituted. So the reaction is called substitution reaction. So the same reaction can also take place with bromine. But remember, the reaction has to take place in presence of sunlight. This is to form chloromethane, dichloromethane, trichloromethane, tetrachloromethane, which we said is one of the examples of solvents or non-polar solvents. So another example of the reactions that we need to look at is the thermocracking. Cracking is the breaking down of bigger alkane into a smaller molecule, liberating smaller molecules, and one of the molecules can either be an alkene, this one is an alkene, and this is an alkane. So this is a bigger molecule with so many carbon atoms, and then it is heated at high temperatures. It breaks down into smaller molecules, into smaller useful molecules, which will produce an alkene, alkane, and sometimes the hydrogen atom can also be liberated. So we can also look at the preparation of methane. They are mainly prepared by this reaction, sodium ethanoate reacting with sodium hydroxide to form the methane, and this reaction takes place when there is also heating. So this is the general method that can be used to prepare alkanes, and we call it decarboxylation, or decarboxylation reaction. So other alkanes can also be prepared in the same way, using the same apparatus where it is heated with soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide. So I'll just leave you with some of the uses of the alkanes, and I will ask you also to make the research and look for other uses of the alkanes. Those are some of the uses of the alkanes, but please make sure you also do some research and get some other uses of alkanes. Thank you so much, dear students. Hope to be with you in the next lesson. Bye-bye.